Hey guys, so today we're going to review Gauss's law. To understand Gauss's law, first we need to go over flux. So flux is basically defined as the amount of electric field E penetrating a surface. So if we just imagine an electric field represented by these lines, and we place a 3D object shaped kind of like a potato into that field, then our equation for a tiny piece of flux through, let's say, an area this small, dA, is d phi flux is equal to E dot dA. Okay, and the dot product means that if we want to calculate that out, that's E dA cosine theta. Okay, and if we want to find the total flux along this surface, this potato-shaped surface, then we integrate using a closed integral, and that's what it is, closed integral E dot dA. And we call this surface, this potato-shaped surface, a Gaussian surface. Okay, so moving on. If we want to derive Gauss's law, so let's just pretend that we have a point charge of plus q, and let's draw a spherical Gaussian surface around it. And let's call that radius r. Okay, and the charge is generating a electric field of E. All right. So using what we know about flux, we can say d phi is equal to E dot dA. And since the E's are all going to be perpendicular to our Gaussian surface, we can say, from there we can say E dA cosine theta, and then cosine theta is going to equal 1. So d phi simply equals E dA in this case. All right, and then if we integrate, phi is equal to d phi, and that's the closed integral from E dA, and we know that E is going to be constant all around this Gaussian surface, so we can take the E out, dA, and then we want to find the total surface area of our Gaussian surface, this sphere. So then we know that the surface area of a sphere is 4 pi r squared. Okay? So if we sub that in, that's E is equal to E times 4 pi r squared. All right, and now we need to find E. And to find E, we use our formula for the electric field generated by a point charge. So E is going to equal Q over 4 pi epsilon naught r squared. That's E on the Gaussian surface. Okay, and we plug all of that back in over here. A lot of things are going to cancel out. Okay, 4 pi's cancel out. Oh, this is supposed to be big R. Our squares cancel out, and we get phi is equal to Q over epsilon naught. Okay, and we also know that the total phi is going to equal the closed integral of E dot dA, just from before, and there we have Gauss's law. All right, so this is always going to be true, but it's not always going to necessarily be useful if we want to calculate something. For example, in this example where we just derived it, we could get rid of the cosine theta because we could say that the electric field would be perpendicular to the surface at all points, and that's not always going to be the case. So generally, you're going to want to use Gauss's law when the shape of your charge is very uniform, and so you can get that cosine theta to equal 1. So when you have a point charge or a spherical charge, something that's cylindrical, and you can draw a Gaussian surface around it like that, and you want to find, let's say, the E at that point. Or if you have a plane of charge, and you want to find the E at a point above it, you can draw a Gaussian surface, like a cube or so. All right. Okay, so that's when you would essentially use Gauss's law. All right, lastly, we're going to look at what if we don't have a uniform distribution of charge. So let's say we have a solid sphere of charge. This is a solid sphere. I'm going to draw inside of it. That's the center, and it has a radius r. And the distribution of charge is unequal. So let's say the charge density rho is going to be r squared, distance from the center, and that's the charge distribution. Okay, so let's start out with Gauss's law. Q enclosed over epsilon naught dot dA. We want to find the total Q enclosed, and what that's going to require is an integral. So we're going to imagine integrating the charge based on small shells of this sphere. Okay, so small shells kind of like that. And the way we're going to do that is take the integral of the density equation, so that's r squared, times the volume, dV, over naught. And since we know that the electric field is going to be constant, we can take that out, and this is just dA. Okay, so we can convert dV into, we can get that into r's by simply subbing in 4 pi r squared dr. And this works because when we have a very, very thin layer of the sphere like this, then that's basically the surface area there times the tiny bit dr, that thickness right here, and that is going to equal dV. All right, that's over epsilon naught E, and this all integrated, that's going to be 4 pi r squared. Okay, and now we're going to pull out the 4 pi, we're going to integrate, solving that out, r to the 5th over 5 epsilon naught 4 pi e r squared. Pi's are going to cancel out. All right, 4 pi's are going to cancel out. If you want to find E, it's going to cancel out here, and E is going to equal r to the 3rd over 5 epsilon naught at a certain distance r from the center. But that's, important to note, that's only when you're dealing with inside this sphere of charge. If you're going outside the sphere of charge, then that would be like our first example when we're just dealing with a point charge that's enclosed within the Gaussian surface. Okay, that's pretty much it for Gauss's law.